Hello, how's it going? It's been busy lately with some stuff. Crazy week. I really only have one goal for today. Um, the plan for today, make one quick tweet on the Pokemon stuff, so we keep that going. And then all I want to do today is fix long horizons in the new algorithm. That's all I want to do today. It should be a relatively simple normalization problem. I think I just was too tired yesterday to think about it correctly. That's all I want to do. If we get that done today, I will be happy because that will push us to where we can move on to a lot of new stuff with Puffer. I'll be able to clear my mind of it and we'll be able to work on what I have planned for tomorrow all day, and it'll be good. We've got some cool new people in the Discord as well. Interesting. Very nice. Let's get this tweet out. This has been doing pretty well. This Pokemon stuff has been doing pretty well. Where's the blog here? I just want to pick something cool from here. What? Can you not, Oh my gosh. He included this as a graph. This is so funny. Man, why would you do that? That's so much effort. I'm trying to think which one would do better on X. What do we think? This is a cool visual. Maybe this one. Did Claude make that mermaid chart? I don't think so. I think that guy did it. Well, I guess it's no longer anonymous, David, but... I think this one will do. Maybe we do this one today, and then we'll do the next one on Monday. Yeah, because then people will see it's a different tweet, clearly. I think it's important to get this right. I'm trying to think what else. I don't think anybody's even done this. Oh, this is a cool little, there's a cool post, but it doesn't have any results. It's like, hey, this would be a cool thing to do. It's a proposal. What's wrong with Twitter's spacing? All right, I think that's a nice post. We'll see whether this chart style thing does decently or not, but it's cool. Cool, somebody's actually in hyperparam optimization. That's cool. I think that's all right, cool. So that works. And we will see. We will see with this. Did this not get posted? Oh yeah, it did. Okay. Now let's talk about the research side stuff I want to do today. I want to at least outline what I'm trying to do once, because it's a little fiddly and requires a lot of thinking, so it's a lot of me just staring at the screen. So I want to make sure that I do this at least once. And maybe this will help me get set up for the day as well. So what I'm going to work on today is part of a new algorithm I've been working on to improve over PPO. That has been attempted like hundreds of times over the last 7 years at this point. 6 years, 7 years, and nobody's done it. PPO is still king. So I think we're actually going to be able to improve on PPO. Specifically, we are replacing generalized advantage estimation. The reason for that is generalized advantage estimation requires 2 tunable hyperparameters, and it locks you to learning rewards over specific horizons. So you can tune these parameters to essentially say, hey, I care about rewards 10 steps out. But then if your environment is complex, and as you learn more, it turns out that there are rewards that are 100 steps out, you're not really going to learn that. So I want to replace GAE with something that doesn't require lambda and gamma and has flexible adaptive horizons. What I've done for this is I have replaced the value function, right, which is typically just output from the neural net, right? Like you have your hidden layers, okay, and then you output your value like this. And so you have hidden, and then you have value. Well, what I've actually done here is I make I call this VT plus 1, and VT plus 2, and then we do this going out, and then we also output, we also have VT standard deviation. So it's variational, and it is predicted over the next many, many time steps. This is the new algorithm. Well, part of it. So what are we going to train this first of all to? Well, at least training this value function is relatively easy. Because we have standard deviation and because we have T, this is just a Gaussian NLL on the V, VSTD, and then rewards. And you have to take in the whole reward vector to do this. But this is how you train your value function. And this is kind of cool because now you're using not just a single float, you're using as many value functions for it as you predict at every time step for training. So this is quite powerful already. But you still need to write down the advantage function, okay? And the advantage function is a little bit trickier. This is what I've been working on at the moment. Because what I want to do is I want to say that the advantage is going to be something like, let me make sure. So this is like y minus v over sigma squared, which is just this thing. Now, this is sigma squared. So I should just even write it that way so it's easier. V STD squared. I want to write something like this. But there's an issue with the scaling of this thing. Like this is a perfectly good advantage formula, but there's an issue with the scaling. So you're going to learn VT standard deviation, right? This is a learnable parameter. But the environment has some intrinsic frequency of reward to it, right? Where you can kind of just predict the mean reward, and you're going to get something that looks like this. If we draw a graph, okay, so this is t, and this is t plus n. So you're going to get something that maybe starts up here, and it's going to end not, where is it? Hang on. Other way around. So you're going to get standard deviation is going to look something like this. Okay, so you're confident at time t because this one's easy to predict. And then up here, this is essentially random, but it doesn't like go off to infinity. It converges to a value. And there's a little bit of noise in here as well. So we want these predictions to contribute 0. Okay, these have to contribute 0 to our advantage function. So we can't just put over v standard deviation squared. This has to essentially go to infinity or something. And then here, we would like to also normalize this so that these sum to 1. And the reason we'd like to normalize these so that they sum to 1 is that this VT is kind of a parameter, right? You can set the maximum number of steps that you can predict out. Like this could be 32, this could be 128, whatever. And the algorithm should basically work the same no matter what you set it to. So you should not have to retune your hyperparameters if you go from 32 to 128. And if you don't normalize, you have to retune because you're summing these or taking the mean of these, and that's going to change the magnitude if you don't fix that. So this is the new algorithm. I think that right now, based on what I've seen, I think that we have a 60 to 70% chance of having this thing work as a general purpose improvement over PPO that you're basically always going to want to use, like everywhere, if we do this thing correctly. So if I can do that, that would mean that Puffer would have the first core algorithm improvement to reinforcement learning since 2017. That would be huge. And it would enable a lot of our research because there's very, very good reason to believe that this algorithm is going to specifically work better for hard environments as well. What is Y in this case? Y is going to be the labels. So I wrote this like a Gaussian process. This should probably be R. So this thing was a pain in the ass to implement as well, because the way that I've been doing this, I had to write a CUDA kernel for this because there's like masking and stuff involved. It's not quite as easy as just writing 2 lines of PyTorch, but I think it's very close. If I can figure out this normalization, I think it should work. And if it doesn't work, then we'll have to figure out why. There should be a reason for that. But I will leave this somewhere. I'll leave this here in case anybody asks. And then we will attempt to figure this out from here. Okay, a couple people are seeing this new post. If anybody wants to go boost the Pokemon stuff, feel free to. Go follow that guy as well here. Why do you think it will help more for complex ends? Yes, very simple. So let's say that you have, let me think, what's a good example of this? I mean, I could even do like neural MMO, right? All right, you have your agent here, and you have an enemy here, okay? And you need to kill this enemy. That's like one way that you're going to get reward. So GAE, you tune your hyperparameters, and GAE tells you, yeah, you just go ahead and set this to, you know, gamma. How do you even write gamma? 0.8. Set gamma equal to 0.8, and you'll be good. Okay, because it's a very short horizon problem. But then you know, that's all well and good. That teaches you to kill enemies. But then over here, you know, you have a resource that you need to get. Okay, and this is way further away. You have to actually have a longer horizon. So if you want to get this resource, 0.95 or something. So gamma changes. Uh-oh. Like, that's a problem, because now you're not going to learn this problem because you're looking too far out, and you're not going to learn this one as easily. So in Dota, this didn't work. Like, PPO broke for them in Dota because of this, and they actually had to anneal gamma over the course of training so that gamma would get larger over the course of training. But they're kind of just applying some like stupid scheduler to this thing, right? This is not like a good way of doing this, and you still have to tune these parameters in all cases. But what I can do with this new algorithm is I can just delete this, right? And I can say, whatever, you know, you're going to have VT through like VN, what is it, T plus N? T plus, I can't write. Okay. And then all I do is I just say, hey, look, this one, sigma 1 equals 1, sigma 2 equals like 0.1, 0.15. It'll just learn this, right? It'll just learn this, like this distribution. And then when it needs to learn the longer one, it'll just adjust this. So it's like sigma 1.1, sigma 2 equals 0.11. And it'll just learn essentially to adapt the effective gamma, the effective horizon on its own. So it's not the episode length. It is the frequency of sub-goals that are defined by the rewards. That is why I think this algorithm is cool. Okay, so now with that said, let's open this up and see if we can actually get this thing normalized correctly so that we can figure this out. Right now, the way I have this thing, this is the CUDA kernel for it at the moment. I am passing in the global maximum standard deviation. Does that make sense? Potential now and P3O curves I've seen make more sense. Takes a bit for the neural net to learn then episode. Yes, it should. Also, note that even on breakout, the version of P3O that I have with 32 horizon, that almost matches PPO performance, like PPO sample efficiency. It takes just a little bit longer, like 10-15% longer. Samples and wall clock. So like we're very, very close, even on an end where it shouldn't really help that much. Like breakout is an environment you would like, you know, the gamma and lambda are very, very accurate because the horizon of the task is basically fixed. It's just break a block. So even matching there is very, very good. And then actually what I should probably do is I should probably compare to like Atari default parameters, right? 0.99 gamma, 0.95 lambda, right? Or whatever it is that they use as defaults. Maybe it's the other way around. I'd have to check. Yeah, that would be the real test. Because if you can beat the parameters everyone uses out of the box, then like that's pretty darn good as well. So currently I passed in the maximum standard deviation. What do you think would be a good end? Yeah, it takes billions of steps, but it runs at 1.5 billion steps an hour, so we'll just do that. Right? That's the cool thing about puffers. We can do that. So apparently I broke something here. I don't know what I'm doing. There we go. 22K runs is crazy. Yeah. It'll be way more than that. I gotta do the full Impulse Wars review for you as well. How close do you think you are on that? As I'm looking forward to that end being merged in. neural net to see and build stuff. Yep, that's about right. That sounds about right. I've actually got like plenty of like core science side tasks that you would be pretty much directly able to help with that will not like drive you nuts, but you'll still be able to learn some stuff and definitely be able to contribute well to the science side here. Like we really want to get a lot of these M's in a spot where we've got benchmarks on them. They're nice and stable for benchmarking. And then I have like, there's a whole list of techniques that need ablations on them to see like, does this technique help? Does that technique help, right? Okay, so this is broken somehow. Also considering finishing lunar lander and maybe bipedal walker. That'd be cool. It would be good. It would be good to have more continuous physics based stuff. Yeah, it definitely would. I tried to do a rocket lander, which is kind of the same thing, and I just got stuck with box 2D being a pain. We'll see how this one does today. I don't expect this one to do super crazy because it doesn't have the flashy visuals, but I wanted to save the next one for Monday. Post something today? Oh yeah, here we are. Autonomous coding. Interesting. Autonomous coding does kind of solve everything, but Interesting. Problem is, it's also the area that's been like the most heavily investigated and doesn't work. Okay, so that was that normalization factor was what was breaking it. Cool. Now if I do this normalization again, just have to wait for experiments. They're only 2-minute experiments, not bad. Oh, hey, that's funny. This is finally the, we got Rune following, that's cool. Oh, his RuneScape.ai is hilarious. One request is you get some kind of controller to be able to understand. Wait. My one request when you do review Impulse Wars is that you get some kind of controller. Oh yeah, a controller. Okay. I can do that. Is it that big of a difference, just the controls? Or is it like I'm just going to be just as bad with a controller at it? Night and day? Okay. Because I do play some games, and I'm stuck in like bronze and silver in every game I play. To be fair, I don't play that much anymore. The only game I was ever good at was RuneScape, ironically. Like the high-end PvE. The mechanics were like way more muscle memory. So this crop totally screws up learning as well. Is this the case? Yeah, this totally screws up learning. What about this? Never played. No competitive games? I mean, I have by far the most number of hours in MMOs. And then as a distant seconds will be like, spread across just the various larger competitive games. FPSs, fair enough. I get bored of every single player game, like very quickly. Never really played many fighting games. Why does this clip mess everything up so badly? Or does it just delay a little bit, let's say? That really breaks everything, huh? I have to see what the advantage values are then. That should not break everything. Green run, good P3O run. Nope, this is oh, this is just I just did this 2 minutes ago or 10 minutes ago, man. This is just like if you don't do I have P3O working with short horizons. I'm just trying to fix the thing that I mentioned before with the advantage normalization for long horizons. That's the only issue. The only issue we have now is normalization. Yeah, P30 works, and it works at like 1,000,000 steps a second. It's just the horizon thing being an issue. And that's not like, the horizon thing is also not a, it's not like a, oh no, you have to tune horizon. It's just, it's a bug with the way that we do our normalization. It's just not designed correctly. Okay, so this doesn't work either. So we'll have to figure out one from here. So after you find a good norm function, tons of testing to find. Well, it depends what the results are, right? I mean, if we get the normalization working well, I think it's like very, very likely that we'll just throw this on everything. And when you tune this and you tune PPO, this will do about as well or better. Here are your values. Gonna drive me nuts. Hang on, you don't clear the buffer though, right? Yeah, hold on, you don't clear your buffer. Let's just add this as a, let's just add this for now, just so it's easier to debug. Because it keeps confusing me. Okay. Is perfect. So this gives us our weightings. And you're telling me that cutting these short screws up learning perf, really? That's like interesting, right? Oh, okay. So this is actually giving you a reasonable distribution over values. See? Is this on Neptune, or did I forget to add it? Forget to add it. Let's see if this clipping messes anything up. It really shouldn't, though. Wait, what's this? There was a gap. That doesn't make sense, right? Man, it's still like, there's still a big difference in perf just by clipping the last one, really? Why do you want to clip it? I mean, fair point. I guess I haven't waited long enough in training to see what the values converge to. But the idea is that if you have a little bit of noise down here and you sum these all up, you're still incorporating predictions. Well, here, if I have like 128 samples and there's a little bit of noise, then like you can actually end up just training on the noise instead of training on the sample you actually care about. It seems like there needs to be some sort of clip or similar. This is 360. So yeah, this still does terribly. That's really weird though. Hang on. How does that even make sense? Is there something I'm missing here where like you don't have to compile the CUDA code? It's loaded from PyBind. It'll recompile automatically. That'd be a funny mistake though if it doesn't. But I mean, no, I can see it clipping at the right values. So here, 50 mil into training, right? We're at about 0.5, 0.05, 32 steps in. I don't see how it's possible that this clip term, that's almost never even been applied because it's so small, screws up training that badly, right? If I comment this, then it works, doesn't it? Or am I wrong? Okay, so it gets slightly better when you reduce clipping, and then magically when you completely delete clipping, it just works. Is that what we're dealing with? Oh, this thing goes negative. That's interesting. Okay, so we can see how low these values get towards the end of training here, right? Something is different though, because this no longer reproduces the original curve. Let's see what this could possibly have been. Well, now I'm confused because this is the same as before where it was solving, right? I'm gonna run this again. Let me go check on something. Okay. What I like to do stage files working on. Yeah, that's fair. Let me see if this fixes it. Oops, wrong way. 05. So that shouldn't be needed. Gotta love CUDA. Breaking on you. Literally have to remove the build files. Okay. Is this the thing that was required to make it work? It seemed like it. Oh, maybe. Yeah, maybe this is it. Oh, yeah. That's interesting, though. So, it wants you to keep some probability mass on this, huh? You get the idea, just your own intuition, just my own intuition. I mean, I've kind of been thinking, like, I've kind of been thinking for a long time, right? I'm always thinking in RL about, like, what are the levers that move things? And GAE seems like one of, like, the big bottlenecks where if you could get rid of it, your learning would be a lot more flexible. Yeah. So it's this. That's annoying. So then I was thinking, how do we get rid of JE? Okay, well, what does JE do? JE gives you this, like, essentially fancy discounting scheme. So, okay, how do we replace that? Well, we have to learn discounting. How do we learn discounting? Well, we can't just, like, you could just learn the one parameter of GAE to be fair and have that adapt over training. That would be an alternative. But I went this way with it. Well, I don't know actually know how you'd learn that one parameter. This seems more sensible. Okay, so let's do this. Now let's go. I want to see what happens when you do 128. Uh-oh. Is this working? Okay. 0.1. Okay, there we go. That's something. See, the problem is all these these low values here. It kind of converges to a uniform-ish. Oh no. It actually goes down more. 782. Kind of fast how the feedback loop is? Yeah. What's the fastest that ran at SPS wise? 2.5 million. 2.5 million with larger mini batches and such. It's fast. I'm seeing now the limitation of subtracting them in. Oh, the original Atari ends? Yeah, it's like 6,000 a core or something. With the original architecture, I think the fastest we got training to was 30,000. So, at least like 30x, around like 30x slower than this. And mind you, the original Clean RL version is like 1,000. So this is 800 times faster currently, and up to 2,500 times faster. Yeah, really, people just did not optimize anything at all in RL for years. It was kind of sad. just not learning a reasonable distribution here, is it? That's kind of nice how this works, where you don't have to subtract anything. But the magnitude difference is not big enough. I mean, it does reasonably well, actually, though, for a first iteration, though I don't think that this thing works generally. If this had a much shorter effective horizon, it wouldn't work. We'll be right back. Let me think about how we can do this. I think that we want something closer. This is way closer to like NLL loss. Yeah, let me think about this. I'll be right back. So, Gaussian NLL. Let's see what this does. What happens to this if you add log of the variance? Doesn't really work. That rewards higher variance, doesn't it? Is there some sort of smoothing I can add? Like if I subtract the min from this, what happens? I would like to have that one tracked, actually. So this actually did kind of close to the original one. This might even be too aggressive. See, why is there like this 6 here? Okay, but up until that, it looked kind of reasonable. Uh, okay, there's something. So 10, and then this decays down to maybe you have to just subtract the mean. It's kind of reasonable. Okay, we're getting somewhere with this. Like, that was a reasonable run, right? What else could we do? We could relativize it. Hang on, can you? Oh, you can't, right? This advantage scale, as we have it defined now, we're overthinking this. Massively overthinking this. I can't subtract the mean value. Divide by the scale. It's still going to be positive or 0, right? Most likely. Yeah, this is still going to be positive or 0. Standard deviation, V standard deviation. Okay, you subtract the max. Then you divide by the sum. And that gets you 0 to 1. Just do this so I can see a little better. Hmm. One, 7. Well, this number should also get more stable over training, right? And this just gave me completely different perf. Right? Same seed. Completely different perf. It's tricky because you can't really just subtract the mean, can you? You know what? Maybe I can find a better value to subtract than the V standard deviation. Maybe I've been looking at it wrong. Hang on. We do have a giant buffer of rewards right here, don't we? I'll just train this for a bit. You might have to subtract the standard deviation of the reward. Oh, 08. Six. That could be something. We might have something here. Huh. This does look good. Continue here. Does it continue to decrease? It shouldn't. Going back up now. I think we have our winner here. We'll see if this works empirically. But what I'm thinking, right? I think this is actually kind of clever. I have my moments. So here's the cool thing with what we can do. Whoops. We'll implement this right now. So if you have what's going to happen is it's going to look something like this. This is going to be your prediction over time of the standard deviation. And the standard deviation in reality is going to be something like this. Right? So if the standard deviation of your prediction is the same as the standard deviation of the underlying distribution, then I believe that means that you have no signal here. But the thing that could happen also, which I think is what was screwing us up on 32 steps, so like if you are at a 32-step prediction, so that's say like right here, I was subtracting this value from the whole distribution. So I was saying, nah, there's no signal here, but there is signal here. There's only not signal when these two things meet. So I need to subtract the standard deviation of the actual distribution, which I have an estimate for, because I have all the samples. So let's just give it that. Yeah, let's just give it that. So instead of giving it V STD max or whatever, we'll do D reward standard deviation. Okay. Error building advantage kernel. This should never be able to be 0 anyways. Hang on. It's gonna be pretty cool. Nams, lovely. What happened here? The heck is... Where do we have Nams? They're ridiculous. What the heck is wrong with this? Oh, I know. I'm dumb. My bad. We'll have to just clean this kernel up. There we go. (1.6), and then it goes down to negative values. We'll try a clip term next. $585, okay. Try with clipping next. There we go. Oh yeah, it's clipping. And the ones that are not getting clipped are E-4, E-5. That looks good. Now it's weird that this does so much worse than the unclipped version. This is probably just the warm-up stuff though, right? There we go. Doesn't seem to be learning very well. $50. That didn't do anything, right? That doesn't do anything either. Really doesn't like this clip factor, huh? Oh no, maybe this isn't it. Okay, so this is not this whole thing that's just breaking it. Good. That wouldn't have made much sense now, would it have? Okay. So this like little bit of uniformity apparently helped at the start before you know the value function. The value function here is very important. What happens if we do a 32 horizon? I mean, this to me looks like mostly stable learning, but it just takes forever to get started. Interesting. And this has learned a very nice, smooth distribution. Very, very nice and smooth distribution. And we have this gets 104. Actually, we can log both of these nicely. This is now possible, like we're in the territory where we've changed it enough that we might just need to retune hypers. And we might just straight up need to retune the hyperparams. This makes sense, right? Yeah. Yeah, this totally makes sense. Well, maybe not. Maybe not. What if I don't do this? What happens? If you get zero advantage for a bit, you just, you just learn the value function. That's fine. So this latest run here, we're gonna just have to rerun the sweep to see. It's hard to say. I think in principle, this algorithm now makes way more sense. It has some properties that were clearly missing before. But ultimately, we will have to see. Let me start working on committing this stuff up. 106. All right, so it's on par. Sweep. Get this token. I think in principle, at the very least, the new weighting it makes a lot of sense. It makes a lot of sense. We'll see whether I'm right, because the current experiment just with the same hypers does not do very well at all, but you never know, right? We changed it a lot. It could require completely different tuning. This is why you need to be able to run massive hyperparameter sweeps. Otherwise, I'd be sitting here for the next week, like wondering if I'm stupid or not. I just get to know if I'm stupid in a couple hours. Let's go check out Neptune. Make sure this works. Okay, great. We'll let this go, and we'll see how it does. I will be probably back later today working on other stuff. Depends. We'll see how it goes. I'm gonna have a long workday planned tomorrow, so might not. But I will be at least checking back on these things. Exciting possibilities. As soon as we get the scaling right, I think we're gonna have something really special here. So if you're interested in following this and other work of mine, Puffer.ai. It's all free and open source. Start the GitHub to help us out. Join the Discord if you want to get involved. And follow on X for more RL announcements and stuff like that.